Okay, so we're going to start with looking at Le Chatelier's principle worksheet. We're going to work through most of the problems that are odd numbers. I'm telling you online. So I'm going to start with number 3, and we'll do number 1 last. Number 3, you have an equation where you have HGO. You had one just like this on your AFL. It was a different equation, but the same concept. HgI4 and 2OH minus. And then we were told that delta H is going to be less than 0. So that tells me that it's a negative value. And this is a multiple choice question where it asks us which of the changes will increase the concentration of HgI4, which essentially means which of those changes are going to cause my reaction to shift to the right. And so one of the things I really want you to try to remember is that when you add something, you're always going to shift away. If you remove something, you're going to shift towards. So when we add, we shift away from wherever we added. Whoa. If you remove, you're going to shift toward. So that means either I need to remove something from the product side or add something to the reactant side. I'm getting the AFL one mixed up with this one, but remember how much we're doing. Okay, so we want something that we can get to shift forward. So increasing the concentration of OH, that would be adding something to the product side. So OH is here on the product, so I would shift away from that. So A will not do it. I'm going to come back to B since that's the right answer. On C is going to increase the mass of HGO. Well, HGO is a solid, so HGO's not going to be involved in anything having to do with equilibrium because solids and liquids are totally excluded from all things equilibrium. So you would not be concerned with that. And so you would skip that one automatically. Increasing the temperature for sure could have something to do with it, and then adding a catalyst is never going to have an impact either. So C and D, I'd want you to automatically exclude because when you're going to add a catalyst, it will have nothing to do with equilibrium expression. It only will get you to equilibrium faster. It's not going to help you in any way as far as shifting it goes. So let's look at temperature. Why does increasing the temperature not the right answer? If it's negative, that tells me that this reaction is what? Exothermic. So does that mean energy works with the reactants or the products? Products. That means energy is here on the right side of the equation. And so that these, when they react, they make energy, and energy can help those to react. So when I increase the temperature, I'm increasing the energy available, making it easier for these to react, so they will, and it'll cause my reaction to shift to the left. I've added something to the right, so it shifts away. So that's why D cannot be the right answer.
Is exothermic always like linked to the products and the third to the reactants?
Mm-hmm.
Okay.
And so then that takes us, the only one left is B, which we know is the right answer. And the reason that HNO3 does make an impact here is because when I add my HNO3, I'm adding H plus ions and I'm adding NO3 minus ions. Well, NO3 is one that's always soluble. So the likelihood is that's not going to be involved unless it's obviously in the equation, and it's not. So H plus has to do something. And what H plus is going to do here is it's going to react with my OH, and they're going to form a precipitate. And they're going to make H2O. And so I'm going to lose the amount of OH that I had in my reaction. So it's going to need to shift to the right to replace that OH. So that's why B is the right answer. Some people also thought of it since I'm making water and adding product, or adding reactant, excuse me. Do you have a question? Oh, okay. Does that make sense to everybody on that particular problem? This would be a good time to ask me a question if you have one. You guys are staring at me with faces that tell me you want to ask a question, you just don't know what that question is. Maybe Amira can help.
So like, how did you know to add HNO3 to the product side and not?
Because there's nothing on the product side that it's going to react with. If I put it with HI, that's aqueous. So they would still just be H plus and I minus ions. Is not going to form a bond with that to make anything else. HGO, it's not going to react with because that's a solid, and then it's not going to react with water because it doesn't have a negative charge to it. So on this side, the one that has the negative charge, and even if you put it with HGI because it has a negative charge, it would be the same outcome. But recognizing that H plus and OH minus are really likely to react because they're going to form water, it's probably one of those things you should just like kind of store in your brain for general helpfulness. But that's how I knew it.
So those reactors, how much does it take? So like, how does that increase the concentration of HCl4? Like, increase the
No, because now what's happened is we've lost, obviously I'm not going to lose all of it, but let's imagine that we did. So now my reaction was at equilibrium, but my H plus came in and pulled the OH out of. So now the reaction needs to return. How did it pull it out?
Yeah, I did.
It did. So the H plus and the OH came together to form a bond, and it made water. And now we just have extra water in my solution. And I'm missing the OH. So is my reaction at equilibrium? In order for the reaction to reestablish equilibrium, it's going to need to shift. And it wants to shift towards where that stress is, to undo the stress. And the stress is we're missing OH. So to stop it from being stressed, it has to replace the OH. So my reaction is going to shift forward. To make more OH, these guys are going to come together and react. And they're going to make OH to replace what was lost. But in making OH, they have to also make these other products as well. So they'll also make more energy, and they'll also make more HGI4.
So when you add something, it's not always shifting because it could be floating.
Well, that's why you have to think about what that's doing. The only way you're going to remove something is probably by adding something. But I'm not adding something that's directly in the reaction. Chances are if you're adding something that's not in the reaction, H plus wasn't in there anywhere, and O3 minus wasn't in there anywhere. So probably they're going to react with something, and then that will have it remove. Because the only way I can remove anything is by getting it to react with something else. Because I'm not going to be able to just, sorry, it's being weird.
When you add something that like has nothing to do with the reaction, that's when it'll shift away. Because
it'll shift towards it.
It won't be. Well,
so you're going to add something that's probably going to be removing something else in your instance.
When can you add something and make it shift away?
If you're adding something that's in the reaction.
Okay.
So if I added HGO or, well, okay, that's a bad example, but I minus or water or any of those, it's going to shift away. Do you have a question?
I was just still trying to figure out how you knew to put it on the product side instead of the reactant side.
Okay, so we've got H plus, we've got NO3 minus, right? So what would be your first thought when you see those things? I don't know what to do. Okay, so then your second thought is, well, I got to figure this out. They're ions, so they're going to react with something. Well, this is a negative ion. So let's say you didn't come up with the fact that it was soluble, so it's not likely to do anything. There's really not anything up there that's a positive ion for it to react with. So let's scooch over to this guy. So this is a positive ion. It's got multiple choices. Let's say it were to react with H plus and I minus. Okay? Hi. Oh, look at you. You're such a kind person.
Let me know if you need me.
I will. Thank you so much. She's so great. I love this open. Or last one. Let me know. I think it's last one. So anywho, those two, if they were to bond together, what are they going to form? HI. Okay, so HI. Is that soluble? Yeah. So is it going to stay a solid? Or is it going to break apart into its ions? So then, would they bond together? No. What's the point of bonding? If they're not soluble, they'll just stay in their ions. So there's not anything on this side for H plus to work with. So that's not going to do it. So then I look over at this side and I see, okay, well, like that's a negative, so it could go with that one. And this is a negative, so it could go with that one. And between the two, I would hope that you would say, if I put H plus and OH minus together, that's going to make water, which would then mean I have less OH in the reaction. So I have to remove it out. Does that help kind of think about how you would figure that out?
So you want to look for something that will make it precipitate?
Mm-hmm. Yep, because if you're adding something that's not directly in the reaction, that means it's going to react to something that is in the reaction.
Okay, so that all made sense, but just like
Great.
one little thing. You said when you add the H plus and it takes the OH away.
Uh-huh.
Where does it go?
It becomes water,
Okay.
and then the
So-
water is just in the
When
solution.
you say it takes it away, I mean you're just saying that like OH minus doesn't exist anymore and it's just H2O.
You have less OH minus than you had before.
Okay.
Cool. I think that's just
That's like kind of like a general rule, kind of. If you like add something to form a precipitate, will the other substance increase?
So that's when you remove something, you're going to shift towards the side that you removed it from. So if I removed OH, I'm going to shift towards where the OH is, which means everything else around it will increase.
Okay.
Yeah. So far, so good? Those are great questions. Other questions? Your faces are making me feel better. All right, then 5. Sound like a plan? Are you okay?
Yeah, you said something that made me Sorry.
Should I be nervous? Where did I put it? Okay, number 5.
Are there any questions like this on test where it's like one almost and one one? Number 5, like.
I know what you're asking.
Oh, this is okay. Well, there are any like those.
Whoa. So I'm
Yeah.
doing the wrong one. We
Yeah.
have 2 number.
Because that one's 1, and the next one's 5.
That's
So
what
I
I
didn't
was
know if it
looking
was one as acting as 5, and then I don't know. I was that's
I didn't know that was. I don't know why that happened. Amira, did you want the actual number 5?
Yeah.
Okay. Jokes. Cole, I do not know the answer to that question off the top of my head. I think the answer is no, but I will happily go check when I'm finished with this if you want to ask me. And if you remind me before we leave, I can tell you that there won't be, and I'll go through and change any that are like that because I do try to take those out of there.
Number 1.
They used to do that all the time on the AP tests, but the new version, they've gotten away from that. So I've been trying to change my questions away to kind of match that, but every now and then I miss them. So that would be a good reminder to make sure I double check. So delta H is negative. So in this particular question, this is not multiple choice, and it's asking us, and this one I actually wrote the answer to A wrong.
Oh, okay.
Does that solve your problem?
Yes.
I did A wrong.
So it's supposed to be decrease.
Whatever I said it the opposite.
Okay.
My explanation was right. I just said the wrong, I think, increase or decrease.
Not.
Does that solve it?
Interesting.
Yeah, I don't know what happened. I was working on this with another person and I realized that I just wrote it wrong. Okay. Does anybody else want to see this problem? Or does that clear up everybody's problems? For number 5A, I had said increase or decrease the opposite way that I meant to say it. Okay, then 7. All right, so 1 and 7 are both very long problems. Is that where you guys want to like spend your time, or would you rather work through some of these other things that we've got going on? Like, I do want to prioritize. How many people want to see me work through number 7? How many people want to see me work through number 1? Okay. How about, do we want to like go through our choices and do quick little votes?
Yeah.
All right. So number 3 on pressure and gases is essentially solving for KP. Changing your equation would be like you're given a K and you make an adjustment to your equation to see how you would quickly change K without having to resolve it, which there's some reminders we could do on that. That would go quick. Solving problems with X versus without, I could just go over like which instances you would do that with. And then number 2 on AFL, FRQ, I don't know what that one is, but if we're doing all of number 2, that's going to be long. And number 16, oh, I'm sorry, that says number 1B on FRQ. So those are our choices. And then we've got number 1 on Lechat and number 7 on Lechat. Pretend like that's what that says. All right, so how many people want to see the changing equation reminder how to adjust K really quick? You can vote as many times as you want. Okay, pressure and gases. Anybody want to see that one? Okay. How about solving with and without X? All right. How about AFL number 2, FRQ? 2. How about FRQ 1B? 4. Okay, Lechat number 1. 4, 5. 6. How about Lechat number 2? That's what I said. Okay, that's a lot of people. Okay, so all right, so
That's the exact opposite of what.
Yeah,
all right, so let's we'll do the changing equations real quick on K, and then we'll work our way backwards. So it's a good thing we did a little vote. So K is always equal to your products over your reactants, right? And so once you've solved for K, you can quickly do some conversions for K in another way. So let's say A plus B is equal to C plus D. All right. So for whatever we do, we solve and we get K is equal to 2. All right. I'm going to put some numbers in here. Obviously, I'm just making this up. Okay. So you're given an equation and you're told a K value that goes with it, or you solved for a K value. Either way. Let's say we came along and I said, now give me the K value for the opposite equation. 2C plus D. So this is literally the same equation. We've just done the reverse of it. Now, it's important that you look at it that way because we still treat products versus reactants. And so what this tells me is that because I reversed my reaction, my K is going to be flipped, right? And now what was products over reactants now became reactants over products. So I'm going to take 1 over K, aka 1/2 would be what my K value is. So you do 1 over K if you're going to do the reverse of your equation. And another thing you can do is you can change your coefficients. You can change the number that's there in front for your coefficients. So let's say for whatever reason, I wanted to make half of what I made here. So I could simplify this down and say C plus 1/2 D is going to make 1/2 A plus B. Now my coefficients have become these halves. The only time you'll ever see that happen really in an equilibrium type problem is this instance where you want to do something to your K value. You could also go through and double it. So let's say we had 2 A's. I'm going to do this opposite reaction. 4B, 4C plus 2D. Okay, so in each of these instances, I'm going to do this bottom one here for a second. Now, since I've changed my coefficients, where are the coefficients seen in the equilibrium expression? There are exponents. So whatever I did to the equation becomes the exponent of my K value. So here in this instance, what did I do to the equation? I doubled it. So I'm going to take a 2 and make that my exponent on my K. So K is going to become squared. Since my K was 2, 2 squared, now my K is 4. So I take what the coefficient was, or sorry, what I did to the coefficients and make it my exponent on K. So on this one, and then I'll get your question. So in this one, what did we do to our equation? We halved it, and how does it relate? And it's the reverse. So if it's both halved and reversed, I need to do two things to my k value. So what are we going to do to my k value? I'm going to inverse it. So it's going to be 1 over k. And because I cut it in half, I'm going to raise k to the exponent of whatever I did here. So it's going to be k to the 1/2, or the square root of k. Okay. So yeah, so then that would be what? I didn't hear what you said. I'm sorry.
Do you want like it?
Oh, you want to give me an answer? You can.
Okay, I didn't know if that was what you're looking for. Or not.
No, I just didn't hear what you said. So that would be kind of the general idea, is those are the two things that you would potentially do to your k value. And like a lot of times I've seen that on the AP test, just a quick 1-point question to finish up an answer. Because a lot of times the last question and the first question are somewhat simple.
How would the question be phrased if you were asked to do that?
It would say, in a different reaction, you were given this equation. What's the k value? Something like that. They're pretty relatively straightforward. And so you would have two choices. You could take your values and plug them into your equilibrium expression, because you probably would have had those at some point. You can solve for it. Or you can do it like this, and it's just a little quicker. All right, let's do number 7 on Le Chatelier's principal problem, because that looks like our next. Oh, with and without. I have to remember number 7. Do we drop an x in number 7? So the quick version of when you would drop an x and when you would not would have to do with, like, I don't remember. I don't know, say something like that. Okay, so let's say you have two different equilibrium expressions that are set up like this. One of them you would drop your x on, and one of them you would not. Which one are you more likely to need to keep your x? This one you're going to have to keep our x. Why would we more likely have to keep the x there? It's a bigger number here, but these two numbers are fairly close together. So whatever is going to happen when I go to solve for this, those numbers being so close tells me that that x value is going to be substantial and is going to make a difference in what that 8 happens to be. So this one, you'd have to use your quadratic formula. Really, you just want to look at your numbers and see how close they are. Make a quick decision. Most of the time, you're getting rid of your x. And I'm telling you, it's just not where I would want to spend your time, mathematically speaking. So if you see you have a problem that's going to take a lot of time, then chances are you can drop your x. This one, those numbers, do you see how they're pretty far apart in those numbers? And especially since that's such a small number, that x value is not going to make a very large difference. So when I subtract, it's still probably going to be 8. Does that help clear that up?
If you're unsure, is it better to just solve it quadratically because you're probably going to do the same answer?
Well, if you know how to do that quickly, go for it. If not, I would actually say to go ahead and drop your x. Because then you get to the end and you're like, well, shoot, I needed to keep it, and you can resolve it then. But like I said, more often than not, you're solving without it. So on number 7 is a good practice because we actually keep the x, and I can show you how mathematically it makes sense because it's quick math. So 7, 6, 7, they're the same problem. So number 6 has like the information for it. So just make sure you read that, and it has the equation that you would use and the solid and all the information that it tells you. Sorry, we're doing Le Chatelier's principle, the problem on the back page. I switched to that, but it didn't make that clear. So if this is my equation, not that one, carbon is a solid, CO2 is gas, and 2CO gas. Solid carbon and carbon dioxide gas, They have a temperature of 1,160 kelvins. They're placed in a 2-liter rigid container, and the reaction represented above occurs. As the reaction proceeds, the total pressure was monitored. When equilibrium was reached, there was still some carbon remaining in the container, and results are recorded in the table below. So A is asked to calculate the number of moles of CO2 initially placed in the container. So if I'm calculating initial values, is an ICE table going to be helpful to me? ICE table is only going to be used when we're calculating equilibrium values. So if I'm looking for initial values, I need to use something else. Stoichiometry or PIV-NERT are the most common ones. And since this is about pressure and they gave me a temperature and they gave me a volume, there's a really good chance PIV-NERT is going to be helpful on that. So I'm going to call it 7A. I'm looking for the number of moles of CO2. And since that was what was placed in there initially, I know at 0 seconds, that pressure had to be based on only CO2 because carbon is a solid and it can't create pressure. Only gases can create pressure. So that means my pressure is going to be 5 atm. And then we already know our temperature and our volume. We're solving for moles, so the only thing left is my R value. Do you remember what your R value is? But it is on our sheet, 0.08206. And we're going to use that one because my pressure is in ATM. So remember your R value, pressure, your R value and your pressure units always have to match. So the next step would just be about solving for N. So if I solve that out, no. What? I heard there was words, but I did not hear. 0.105 jokes. Your 1111 nonsense confused me. And that's moles. Oh, tired. All right, so I have 3 significant figures in 5 and in 2 and in 1,160, I think. And then that one's got more than 3 significant figures, so my answer needs to have 3 significant figures. And so that's going to be moles of CO2 because the pressure that we used here was about CO2. And so my answer to number 1, or whatever, A there, is just going to be calculate your moles of CO2. I skipped writing the equilibrium expression. Do we need to do that? Let's do that. Questions about PIV-NERT? When would we use PIV-NERT versus an ICE table? When we're not at equilibrium. Yeah, if you're looking for initial values. If I were looking for my equilibrium values, then I would use my ICE table. I'm going to keep that there because I think I'm going to need it in a minute. Okay, so going back, I have to write the equilibrium expression for Kp. So it's products over reactants. So my products are CO. And since it's for pressure, I'm going to do the pressure of CO squared because its coefficient is 2. And then on the bottom, I'm just going to do the pressure of CO2. I don't have to include the carbon because it's a solid. So I should never include a solid or a liquid in an equilibrium expression. For Kp, you're going to be including things that are gases. Well, if it's a KP, you'd only have an equation that's gases. So those would be only gases, but I want it to be consistent. Questions on that? So far, so good? All right, so then if we look at B, for B, we were told that our reaction at equilibrium, okay, so now I've moved to equilibrium, the partial pressure of CO2 just means the pressure of CO2 is 1.63 atms. I want to know the pressure of CF. So on 1 or BI, I suppose, then it seems like that's the only information I'm given. And the thing about it is you're actually given more information because you have this data table. And at this data table, it told you your total pressure, and it told us our total pressure is 8.37. So you can recognize it's going to get equilibrium when you have constant pressure, your concentrations aren't fluctuating anymore. They don't have to be the same as each other, but they don't fluctuate. So remember that graph leveled out. If your temperature leveled out, if your pressure leveled out, anytime you see something consistent that you can measure, that's going to be your at equilibrium. Plus, it told you that this reaction ran until it reached equilibrium. So in the paragraph, it told you the end was equilibrium. So we've got 8.37 is my ATM, and that's my total pressure. And so that pressure is going to be based on both the gases that are in the container. So if my total pressure is 8.37, I can figure out what the two pieces are just by subtraction. Because 8.37 minus 1.63 will tell me what's left over, and then that's my pressure of my CO. So far, so good. And then I think the next question asks me the value of my equilibrium constant. Well, now I know my pressure at equilibrium for both of my values. And so I'm just going to plug them into that equilibrium expression that we just solved or just created. So my pressure of CO is 6.74 squared. And my pressure of my CO2 is 1.63. Be careful on this one. I see a lot of people make mistakes because your CO and your CO2 are just so similar. And so then when we solve it out, you get 27.9. I'm going to label it as ATM since KP can be in different pressures. Questions? We doing okay? So I just love it the most when you ask questions, even if you just want to clarify, restate things. So far, so good? We get how we move from BI to II?
So if we have a liquid in that equation, would we still not include it?
Correct.
Okay. So just solid.
Yep. Yep, you're exactly right. Okay, then if we were to move on to C, C says if a suitable solid catalyst were placed in a reaction vessel, would the final total pressure get increase, decrease, or stay the same? Well, because this is an equilibrium reaction, catalysts don't have anything to do with equilibrium. So you would say they would stay the same because the catalyst does not cause the reaction to shift left or right. I don't know. Catalysts don't do anything.
Why?
Because remember, the catalyst job is to change the activation energy. So in the forward reaction, it has the same activation energy as the reverse reaction because their energy is going to be the same. It's just, and so when the catalyst removes that activation energy, it's going to affect each side equally.
Okay.
Even if it did change the K, wouldn't the total pressure still stay the same?
Why?
Because I don't know, would it not stay the same?
No, because you've got a different number of moles on each side. So if the catalyst did shift left or right, then you would have more or less pressure. Yeah. Okay. So then D, I see a lot of people run into trouble with this because they kind of throw numbers at you. And then it says, predict whether the partial pressure of CO2 will increase, decrease, or remain the same as your system approaches equilibrium. So that kind of sounds like a Le Chatelier's principle problem, but they really didn't give you a ton of information. They told you what your partial pressures were for both. So actually, some people used that as adjusting your total pressure because they took the total pressure now versus the total pressure before and thought about how pressure changed. But my recommendation to you, and I'm just saying that would be fine. You could do that. That's an acceptable answer. They gave you the partial pressure values. And so you could plug them in to your pressure equation and see how what we call Q relates to the K value, because you found the K value earlier. And so you could solve for where you are now and to see how you could get to equilibrium. So my pressure of CO over my pressure of CO2, and I know they're both 2. So 2 squared divided by 2 is going to give me 2. And so if my Q value now is at 2 atm, how does that relate to the K value, which shows me the ratio at equilibrium?
Where's the 2 from?
From the problem right above it, it says in another experiment involving the same reaction, a 2-liter container initially with 10 grams of carbon and CO and CO2 each at a partial pressure of 2 atm. And so since it says there that each is a partial pressure of 2 atm, now you know where you are. So then I took those and I plugged them into my K value to see where we are now. How does that relate to my K? It's smaller, right? So that means I need this number in order to get to equilibrium. What has to happen to my number here? It has to get bigger. And since between these two, in order to get 2 to be bigger, my CO is going to have to increase. So my products are going to have to increase, which is going to make my CO2 decrease. So is my reaction going to shift left or right? Right. And so for CO2 specifically, what will happen to the amount of CO2? And it's going to decrease. Sorry. Okay. So one thing that I just want you to kind of think about is, I don't know. Do we feel okay about that? Do you guys want to do 6 real quick or 1 real quick? No? Yes? Are we feel done with today? There's a couple of the questions on the test where I have you look at a reaction and kind of guess which way it's going to shift left or right based on like the color changes. So let's just say hypothetically that this side of the reaction was blue and this side of the reaction was yellow. I'm just curious. If I were to add CO2, which way is this reaction going to shift? So if I add CO2, I have stressed which side of the reaction? The left. So then to undo that stress, what has to happen?
It goes to the right.
It's going to shift to the right. And so what color is my reaction going to change? To the yellow. What if I removed CO2 by reacting it with hydrogen and it made carbonic acid? Yeah, it'll have to shift to replace that lost CO2, so it's going to turn to what color? Blue. So far, so good?
That sounds like a fun lab.
Well, yeah, it would be fun. That was the one we were going to watch virtually, but we decided not to. Write a lab report over it. Said you could do it and write a lab report over it. Okay, you guys feel good? I'm going to call it a day. I'll leave this on the board and see